today. So we have Tamara Hogan, and I'll let you take the stage, Tamara. Thank you.
All right, can you see my screen?
Yeah.
All right, so I'm good to go. Ready to start? Yep, cool. So I'm going to be talking today about what are called planar algebras. And the idea of this talk is to kind of just give like a rough and ready introduction to what a planar algebra is, without requiring much background at all. So the plan of this talk is that I'm going to start off by giving the historical motivation for why this came up in the first place. And then I'm going to motivate kind of like an intuitive idea of how to think about it. I'll then give the actual definition, which is far more detail heavy and not as intuitive, and then finish off with some examples of where this actually shows up in the mathematics. So the original story here is that this planar algebras were first brought up by Vaughan Jones in a preprint in the late 1990s. That preprint never went on published despite being incredibly influential in the field. He was interested in studying what are called subfactor algebras. And subfactor algebras arise in the study of von Neumann algebras. And I'm not going to give a full definition here, but von Neumann algebras are a specific type of algebra of operators on Hilbert spaces. And then a factor in a von Neumann algebra is a von Neumann algebra whose center contains only multiples of the identity. And a subfactor is a subalgebra of a factor which also contains the identity. And all this is to say that it turns out that subfactors can be studied as a particular type of what Jones called a planar algebra. So that's the history of how we ended up with the definition I'm eventually going to give. So the idea is usually when we think about operators and functions and anything, we think about them in a linear way. And what I mean by that is you have a function, say you've got a function f with 2 inputs and 1 output. You plug that in to a function g, which has 1 input and 3 outputs, and into a function h, which has 3 inputs and 2 outputs. We think of our functions as being stacked on each other in this kind of linear top-down way. And the idea of a planar algebra says that instead we can do this in what we call a planar way. And that says that when we join our operators together, the only thing we care about is that the connections between them don't intersect when we embed them in the plane. So we don't care about directionality, we don't differentiate input and output, we just care about the fact that our connections don't intersect each other. So this gives an entirely new way of thinking about kind of like tensoring together operators or functions in an algebra. So with that said, we can kind of get into the actual definition. So again, this very concise and not very illuminating definition is due to Vaughan Jones in his 1999 preprint. And the definition is that a planar algebra is an algebra over the operad of planar tangles. And this is a not very illuminating definition, and I'm going to kind of unpack it step by step to build up to understanding what this actually means. So to start off with, we need to know what a planar tangle is. So we can kind of build this up too. So a planar tangle T consists of a series of data. And the first step on that data is what we call a disk with n holes. And this is one, you can see on the picture here on the right, we have one big disk, which we call D, and it has a series of smaller numbered disks cut out of it. And basically, to formalize what this means, we have a 2-disc embedded in the complex plane, which has removed from its interior a series of disjoint 2 discs. And then on these discs, we have what we call a marked base point. You can see here the little asterisks on the disc. We give a base point on each disc that allows us to kind of like give a sense of orientation on the disc. And then additionally to that, which I've marked in red in the picture here on the right, we have a set of points on the boundary of each disc, which we can kind of naturally order from the base point. So I haven't written the labels here because it clutters it. But if you think about on this outer disc from the base point, we can order clockwise by 1, 2, 3, 4, 5, 6. And so each base point is kind of naturally labeled from each point on the boundary of the disc is naturally labeled from the base point. And then finally, we have an embedded one manifold such that the boundary of the one manifold is in bijection with the labeled points on the boundary of the discs. And so you can see here marked in green, we kind of have copies of the interval and copies of the circle embedded in this kind of cut out disk space where any boundary on this one manifold is connected to the marked points on the disks. Now, this is hard to formalize, but 2 planar tangles are considered equal if they're isotopic to each other. And by this, I mean, if you can get from one to the other by kind of pushing the strands around without causing any intersection. It's really annoying to actually formalize the definition of that, but that's morally what's happening here. So that's a planar tangle. The planar tangles is the set of all of the things we can encode with this set of data. And so then we get to the next step of the definition is what is the operad of planar tangles? And I'm going to give a little rough ready definition of an operad here because I'm not going to assume it in this context. So an operad is an algebraic structure, I'm going to call it here P, is so it's any algebraic structure which is equipped with a family of maps, which I'm going to call circ I, where I is a positive integer. And each of these circ I's is a map from the tensor product of the operad to itself with some little rules that I'm going to ignore. And colloquially, if we have A circ I B, what that means is insert B into the ith part of A. So obviously here we have to have some notion in our algebra of what the ith part of A means, but that's pretty much in a nutshell what an operad is. Now there's an immediate notion of this for planar tangles because we have in a planar tangle, we have these numbered disks. So we have this notion of what the ith part of a planar tangle is. And so if we have 2 tangles, T and T prime, then T circ I T prime means inserting T prime into the ith circle of T. Now, obviously, there's some coherence rules here. So for this to work, the number of points on the boundary of the ith circle of T has to equal the number of points on the outer disk of T prime. So you can kind of connect up the points on the boundary of one circle to the points on the boundary of another circle and sort of connect them together. But other than that, you kind of just shrink down T prime and insert it into this ith circle. So I've got here an example where I've got 2 tangles on the left and right, and we're going to circ 1 them. So this tangle on the right here You can see it has 4 points on its outer disk, and these 2 strands on the top here of the first circle, we're inserting into this circle here, and you can see that the 2 strands to the right of the base point here connect here and here, and then this lonely strand on the bottom here gets connected to this loop and creates a circle. So adding all of that together, we get this tangle down here on the bottom. And the collection of all planar tangles plus this family of circ I operators gives the operator planar tangles. So now we can finally get to what actually is a planar algebra. So a planar algebra is an algebra over the operator planar tangles. So what do we mean by an algebra over the operator? So an algebra P over our operator planar tangles is given by a series of vector spaces where we call P0, P1, P2, etc. So a set of vector spaces which we index by positive integers. We call these box spaces, which is coupled together with what we call an action by planar tangles. If you're more of a representation theory person, this action by planar tangles says that algebra P is a representation of planar tangles. I'm not a representation theory person, so I'm not going to do that. So what we mean by this action by planar tangles is that for any tangle T, which has n0 marked points on its outer disk, and then n1, n2, such and such, nr points on its 1, 2, 3 through r disks, we have a multilinear map ZT, which goes from the n1, n2, n3, so nr box spaces to the n0 box space. So we have an action of this tangle T on a series of box spaces, which gets us into another box space. And this multilinear map has to be coherent with the notion of the planar tangle operad composition we just discussed. And so what that means is if we have 2 tangles, T and T prime, then Z of T circ I T prime has to be coherent in some way with ZT and Z of T prime. So if we give an example here where we have an element F, which is in our 7th box space, an element H in our 4th box space, and an element G in our 5th box space. And we have this tangle T here, which has 3 input circles. And the first input circle has 7 marked points on the outer, the second input circle has 4, and the third has 5. Then ZT of FHG essentially just means we've inserted F, H, and G into those input circles. So we kind of like decorated the input circles with our different components. And this gives us a new component in the 1, 2, 3, 4, 5, 6. This guy is in the 6th box space. It's the 6th box space of our planar algebra. So with all that being said, we can finally actually discuss concrete examples of this. And I'm going to give 4 concrete examples of it today. The first one is Tangles itself, which will be immediately obvious. We then have what are called temporally leave algebras. which are not my area of expertise, but I think they're worth mentioning. And then we have some concepts from knot theory. We have usual tangles and virtual tangles. So to start off with, we have the easiest example of a planar algebra is planar tangles themselves. So this is just the collection of all planar tangles. Planar tangles. Where plus the action by planar tangles is just given by the usual operatic composition. And you can see here that the box spaces, so we have the box space Pn is given by planar tangles with n points on the outer disk. So this is just a really trivial example just to motivate that this is a thing that exists. It isn't just a random notion. So the next concrete example are temporally leave algebras. And Wikipedia tells me these come from statistical mechanics. And they also have to do with what's called wavelet theory, which is the study of wave-like motion. Totally not something I'm familiar with, but that's cool. So the temporally leave algebra, which we denote TL delta, that's not a delta loop, is generated by the set of planar tangles with no input disks. So essentially the only information we have is the outer disk and an embedded one manifold. And when I say generated by, I mean you take all of the different possible planar tangles with input disks and apply the planar tangle action, which here is just given by tangle insertion. You repeat that over and over, and anything you can generate by doing that is in the algebra. And it has the relation here that closed loops, so embeddings of the circle, are equal to given by scalar multiplication by scalar delta. So this first diagram here is a generator. You can see we just have the one manifold embedded into a disk. There's no input disks cut out in the middle. And the second one here, you can see we have two closed loops in the tangle. And so that goes to multiplication by delta squared without those closed loops being there. So we can now go on to talking about more not theoretic uses of this, which is where my interest comes in. And so we go to usual tangles or U-tangles. And a U-tangle is an embedding of copies of the interval into the two disks across the interval, so essentially into a solid cylinder, where we have the endpoints of the intervals are attached either to themselves, so we create a copy of a circle, or to the boundary of this, to the outer edge of this cylinder. And we say that two U-tangles are the same if they are ambiently isotopic. So again, if we can push the strands around without intersecting them, then anything we can get by doing that is equal. And so you can see an example here, badly drawn, where we have the points on the outer edge, and you can see they're tangled together. Now, contained in the set of all U-tangles, we have knots, we have braids. We have any other usually knotted objects that you might be interested in. And this is useful because we can generate all usual tangles as a planar algebra. So we have two generators. We have the overcrossing and the inverse crossing. And again, when I say generators, I mean that you take these two generators, if you imagine these guys as little planar tangles, then you just apply the planar tangle action over and over again, and anything you can generate by doing that is in our algebra. And then after doing that, we have a set of relations, which if you're into knot theory, you'll be familiar with. Here we have R1S, R1S or R1 spun. This comes from the fact that both ends of a strand are connected to the outer edge of the disk. And so you kind of can't, if it's looped over itself, you can't pull it straight. And this essentially means this comes from framing. So we're dealing with like framed knots, framed links, essentially. But then we just have the normal Reidemeister 2 move where the overcrossing is inverse to the undercrossing and we can pull them apart. And then we have Reidemeister 3 here where if a strand is underneath the crossing, we can pull it past the crossing. So this generates all usual tangles, and so we can contain in here all knots, all braids. And what's useful here is that this is a finitely generated algebra, which means that we can easily, it makes it a lot easier to generate knot invariants. One of the problems with generating knot invariants is that knots are not finitely generated as an algebra, and it makes it really, really annoying. So this is actually where the Jones polynomial comes in. This is where the Jones polynomial originally came from. And a whole bunch of other knot theory stuff deals with usual tangles because we have this finitely generated algebraic structure. And so you can see here, you can see here where I've got the dotted line. This wouldn't be included when you're just generally thinking about it, but the dotted line here, you can see where our generators are plugged in and then they're connected together by a planar tangle. And the planar algebra action here is given by the usual tangle composition. So again, this is where the Jones polynomial comes from, and it's generally super useful for knot theory in general for providing a finitely generated structure for a bunch of tangled objects. So then we have the slightly more complicated and harder to draw virtual tangles or V-tangles. And a V-tangle is an embedding of copies of the interval into a thickened surface of genus G, SG across the interval, where SG is the compact orientable surface of genus G. And basically what this does is that we have our usual braiding on the surface where we have an overcrossing and undercrossing, whatever. But then we also have the situation, you can see in green here where I've circled where the normal braiding happens. But then you can also have a situation where one strand is on top of, one strand is on top of the torus at the same time as another strand is on the bottom of the torus. And so when we project down to the plane, these two strands intersect, but they're not actually interacting with each other at all in this thickened surface. And so what we do is we call this a virtual crossing, and you can see where it's happened here. And a virtual crossing occurs when strands are on either side of the surface we're using to embed the tangle in. And so when we project down, they don't interact. So as a planar algebra, these are a super easy extension of usual tangles, where we just add one new generator. So we have the overcrossing and undercrossing from the usual tangles. We add one new generator here, which we call the virtual crossing. And then a series of new relations where we have the virtual Reidemeister 1, virtual Reidemeister 2, and virtual Reidemeister 3, plus this mixed relation, which says how virtual crossings and usual crossings interact with each other. And so again, you can see an example here. We have a series of generators connected together by a planar tangle. And planar algebra composition here is again given by the usual tangle composition. And these guys here have their own whole world of knot theory, which extends from usual tangles, where we have contained in here, we again have virtual knots, virtual braids, etc. And in some ways, the virtual knot theory kind of makes the usual knot theory work better, or there's some things in usual knot theory that we use that kind of don't work all the way, but virtual knot theory like completes it in a way. They have their own whole world of virtual knot theory, which is cool in its own right. And so that's the end of my concrete examples. I just wanted to finish off today by mentioning that there's a whole bunch of other things that aren't knot theory related that these planar algebras show up in. And the first one is that a whole bunch of different Hopf algebras are isomorphic to a specific kind of planar algebras. So planar algebras can kind of give a concrete algebraic definition of Hopf algebras, which are not simple to write down. They can also be used for Fourier transformations of certain things. Biprojections, they show up heaps in quantum algebra. There's so much knot theory. My PhD project deals with knottings of ribbon tubes in 4 dimensions, which is bananas to think about any other way, but it's super simple to think about using planar algebras. And there's just a heap of other stuff. So I kind of just wanted to use this talk today to just introduce you to a fun algebraic tool which shows up heaps in topology. And that's all I've got for today. So thank you for listening.
Thanks, Tamara. Are there any questions?
Yeah, I have a question. I actually have a couple of questions, but I'll start with one. So you said this is like an algebraic tool for studying like U-tangles and virtual tangles. So is there like a result about U-tangles or virtual tangles that you can prove using this planar algebra idea that's like much easier in this algebraic construction than it would be otherwise? Like, do you have an example?
So proving that there is a universal not invariant for, like, there's a universal invariant of U-tangles or like these usual knotted objects. It's super hard to do unless you have a finitely generated algebraic structure. When you have a finitely generated algebraic structure, it turns into a problem about completing by the augmentation ideal. And when you don't have that, it's just like, it's kind of like you just have to keep trying things until it works. Like, for example, for knots by themselves don't have a finitely generated algebraic structure. There's no combination of operations which allow you to generate all knots by themselves, but extending to this U-tangle universe gives you the power to do that, which is, yeah, helpful.
Yeah, cool, thanks.
Were there any other questions? Or Elena, you can ask your more questions.
Okay, great. Yeah, I'll ask another question, if that's okay. So you said right at the start that these were originally introduced because they're a way of studying, I think it was subfactor algebras. Can you say a bit about that connection? It's okay if it's not at all obvious.
So subfactor algebras, like, they deal with operators in Hilbert spaces, and basically, like, this planar algebra way gives us a way of talking about connecting together operators. Like, you can think of these think of these like these FHG, you think of them as operators on a Hilbert space. And there's a specific type of planar algebra that's called a subfactor planar algebra. And it has some generators and relations, but it essentially generates all of the different ways that these subfactors present as, they generate all of the different ways a subfactor can exist. And you can then draw a line between these general subfactors and the subfactors in your specific von Neumann algebra. Like I said earlier, it's not my specific area of expertise. I'm more than the knot theory side of things, but it is super interesting.
Sure, no, that's cool. Thank you.
Great. If there aren't any more questions, let's thank Tamara again. I'll stop the recording there.